All right, guys, it's our last lesson for Unit 4. It's Lesson 10. It says Part 1, but we're not going to have a Part 2 to this, so this is our last lesson here. We're going to talk about a question that's actually pretty common on your AP exam. It's called a linear approximation. It's particularly common on the FRQ section. So we'll talk about what a linear approximation is, and then we'll talk about how to use that to estimate the value of a function at a specific point. Okay. So first of all, let's go ahead and start off with a story problem here to kind of give us a basis for understanding the concept. So suppose we have a bicyclist who is accelerating as she coasts downhill. So at 0 seconds, meaning right at the beginning of this time, she's going 3 meters per second. Now, how far will she travel from 0 to 1? Well, if she's going 3 meters per second, you might be thinking to yourself, okay, if I'm going from 0 seconds to 1 second, that's a total of 1 second. And if she's traveling for 1 second and she's going at a speed of 3 meters per second, well, that would be 3 meters per second times 1 second. And so the answer will be 3 meters. Okay, let's look at another one here. How far will she travel on the time interval from 0 to 2 then? Well, if she's traveling for 2 seconds at 3 meters per second, then for both of the seconds in there, she would travel 3 meters. So that would be 3 times 2, which is 6 meters, right? But there's a little bit of a problem here with this story problem. Let's do one more, actually. I forgot about this one. How about from 0 to 3? Well, after 3 seconds have gone by, if she's going 3 meters for every second, well, then she would travel 9. So for the first second, she went 3. For 2 seconds, she went 6. And then for 3 seconds, she went 9. So now the problem is, why is this technically not accurate, though? The reason this is not accurate is because of something that's mentioned up here at the beginning. It tells us she's accelerating. Sure, she's going 3 meters per second, but if she's accelerating, that means as time goes by, she's going faster and faster and faster. So for instance, on the time interval from 0 to 1, she's going pretty much 3 meters per second, but by the time we get from 1 second to 2 seconds, she's probably going faster than 3 meters per second. And then by the time we get to the third second, she's probably even going faster. So will she actually have ended up going more or less than our first estimates? And explain why. Well, she'll probably have gone more, right? Because since she's accelerating, she's going faster and faster, then on the time interval from 0 to 3, her speed overall is probably greater than 3 meters per second because her original speed was 3 meters per second. And over time, it's increasing. So by the time we get to 3 seconds, she's going faster. So her average speed is actually probably faster than 3. So it's going to be actually greater. She'll have traveled actually farther than 9. So that would be our explanation there. But, you know, how off would that be? I mean, especially if we want to know how far she traveled for the first second, right? Well, she probably went about 3 meters. If she's going 3 meters per second, 1 second went by, she probably went 3. And after 2 seconds, probably a little bit more than 6, not that much more. But by the time you get here, our estimate probably starts not being very accurate anymore. Instead of being 9, she probably went more like 10 to 12 meters, or maybe even more. So the farther we let this go on, the less accurate it becomes, right? Because the fact is that she's going faster and faster over time. So here is the bicyclist's actual position. So at 1 second, she's here, which is just below, like about 5. Looks like maybe this is 5. So about 3 meters, right? That's what we thought. But by the time she gets to about 2 seconds, she's probably about at 6, and by the time she gets to 3, it says here maybe like 11 or 12. So there's her actual position. The fact is, since she's going faster and faster, this is a curving line. It's bending up because every second we go, it goes a little bit higher than it did last time, which causes it to bend. All right? But we knew how fast she was going at the very beginning. We knew that at the very beginning, she was going 3 meters per second. So this red line here has a constant slope. Over 1, up 3, over 1, up 3, over 1, up 3. Okay? So here's the bicyclist's position based on a constant speed. And so you can see here, as time goes on, the difference between her actual position and our estimated position is getting bigger and bigger. And by the time we get to 8 seconds, that's quite a big difference, right? But the closer we are to the original amount, the better that the red line and the blue line are pretty much the same thing, right? So, how can you tell by looking at the graph if the tangent line will give us an overestimate or an underestimate of the actual y values of this function? Well, you could tell that the tangent line is going to give you an underestimate because it's under the actual curve. So when your tangent line is under the actual curve, then your tangent line will give you an underestimate. What would the curve of the position function look like if the tangent line would be an overestimate? What kind of a curve would have an overestimate tangent line? Can you guys imagine that? An overestimate tangent line would have to have a curve that's bending in a downward direction like that. In that case, your tangent line, which I'm trying to draw here, is kind of hard. There we go. In that case, your tangent line would be above the curve, and that would be an overestimate. Okay, so this is what we call a concave up because the graph is bending in an upward direction. And this one is what we call a concave down because the graph is bending in a downward direction. So when your graph is concave up, a tangent line will give you an underestimate. And when your graph is concave down, a tangent line will give you an overestimate. Now let's think back to that bicyclist story really quick. How can we change the story of our bicyclist on the last slide so the tangent line would be an overestimate instead of an underestimate? Well, remember, the reason why it was an underestimate was because she was actually going faster and faster. So if I wanted my tangent line to give me an overestimate, then what we would want for her to be doing is to be going slower and slower. And so to change the story, we could say, okay, well, we have a bicyclist and she's been riding her bike and all of a sudden she comes to a hill that she has to start driving upwards on. So if she's just coasting, as she comes to that upward incline, her bike's going to start going slower and slower. And because of that, any estimates that we use based on her original speed will actually be overestimates because she's going slower and slower. All right, so what is a linear approximation? A linear approximation is when we use a tangent line, which is a linear function, to approximate the values of a function, and that's what we call a linear approximation. So here I've got this curve, but on top of it I've got this straight tangent line, and that tangent line is a really good estimate for this curve. Matter of fact, you guys can barely tell the difference between the straight line and the curve on this entire region. So about from maybe like 0.5 to about 1.5, the difference is so small that we can't even tell there's a difference. Now by the time you get out over here, there's such a big difference that maybe our tangent line is not a very good estimate anymore, and we'd want to get a tangent line that's a little bit closer. But there's the idea. The closer we are to that point of tangency, the better of an approximation the tangent line will be for the real curve. So let's look at some fundamental facts about linear approximations. So first of all, the y values and the slope of a tangent line can be used to approximate the y values and the slope of a function. Okay, so here's my function, and I put a point of tangency right there, and I draw a tangent line at that point, then this tangent line can estimate for me what my y values are and what the slopes are in that area because the red line and the green line are just so close to being identical in that area that the slope of the tangent line and the y value of the tangent line should be pretty much the same thing as the slope and the y value of the green line. Okay, so that's our first fact. The approximations are better for x values that are closer to the point of tangency. So the closer we are to the place where the red line actually touches the green line, the more accurate the red line will match the green line. And in fact, at that point where they touch, they actually have the same exact y value and the same exact slope. So the closer they are to that point, the more accurate they match. But if they're actually touching at that point, then they're actually exactly the same. Next, we saw that if a function is curving upwards, concave up like this, then a tangent line will give us a underestimate because it's underneath of the curve. And if our curve is concave down, then our tangent line will give us an overestimate of the actual function. Finally, if the function is curving down, so that's just, sorry, that was the other half of it. Okay, so there we guys go. So these are fundamental facts about linear approximations that you want to be aware of. Okay, so why don't mathematicians just use the actual function rather than a linear approximation? So for instance, we're going to have problems like this where I'm going to say, okay, find f of 2, but don't actually find f of 2. Instead, estimate it using a linear approximation. Well, why would I want to estimate it with a line whenever I can just plug it in and get the answer? Well, the reason may be because you don't know what the function is in the first place. Like, for instance, with our bicyclist issue, I don't know what function actually shows her position. All I know is I know her speed at that point, and so I can create a tangent line and estimate her distance that she traveled. So sometimes you just don't know what the original function is. So if you don't know what the original function is, but you do know its rate of change at a given point, then you can find a tangent line and use that tangent line to estimate the values of your function at that point. Also, as you know, in everyday application of mathematics, estimations are quicker and they're usually sufficient. Okay, so if you're going into engineering or something, they actually do use linear approximations to estimate something known as error propagation. Whenever you're designing something, nothing's ever designed perfect, and so there's always little bits of error involved, and because of that, you want to minimize your error, but nothing's ever going to be perfect. And so what engineers will do is they will use linear approximations to get as close to a useful and good enough estimate whenever a perfect one is not possible. Okay, so now that's the background. That's what linear approximations are. So now let's go ahead and start jumping into some of the problems you're going to see. Now, this slide here, example 1 and student practice 1 are probably the most important part of today's lesson here because this is the kind of stuff that you're going to see on your FRQs, okay? Both on the test that's coming up on this week and also on your AP exam. So now, it says, use a linear approximation at x equals 1 to estimate f of 2. Use a linear approximation at x equals 1 to estimate f of 2. So let me give you guys a little bit of background here. So for instance, what if I asked you guys to find f of 2? You don't need to write this, just watch. Well, that's ln of 2. And well, that's kind of a pain in the butt because I don't know what ln of 2 is. I would need a calculator to get that answer. But what I can do is I can do a linear approximation to estimate what f of 2 is, and I actually wouldn't need a calculator at all. So I'm going to show you guys how we can estimate what f of 2 is so that we don't need a calculator and we can get an answer that's really, really close. Okay? Now I've broken it up into 2 steps. Now, me breaking it up into 2 steps like this is just me teaching you and being nice here. But in reality, the only thing they'll say on your FRQ is this. But these are the 2 things you have to do it. All right, so the first thing you'll need to do to get a linear approximation to estimate this value is you're going to need to find the equation of the line that's tangent to your function at x equals 1. Okay, so they want us to do a linear approximation at x equals 1. Okay, now to find the equation of my tangent line at that point, we need a couple of things. We need an x value, we need a y value, and we also need a slope. Okay, so we've got our x value, it's 1, but now we need our y value. To find your y value, just plug it into the original function. Now this is better than plugging in 2, because I know what ln of 1 is. ln of 1 is 0. So my y value is 0. To find your slope, you're going to need to find your derivative of your function. The derivative of ln is 1 over x, and then you're going to plug your x value in. So 1 over 1 is 1. So there you go. So you take the x value at the point that they indicate up here. You plug it into your original function to find your y value, and then you plug it into the derivative to find your slope. Once you have those 3 things, then you have enough information to write your tangent line. You guys might recall the formula for a tangent line looks like this. You're going to put the m where it's set. Where you're going to put 1 where the m is at, and where the x1 is, you're going to put this number, which is 1 again, and then for the y, we're plugging in 0. And so if we simplify this expression, I end up with x minus 1, y equals x minus 1. So there's the equation of my tangent line. Now, before I go any further, I just want you guys to know what I just did there. Okay, so let me give you guys a picture. Now I'm going to put the actual graph of ln up there. So that's the actual graph of ln. But what I just found here was the equation of the line that's tangent to this function at x equals 1. So here's where x equals 1, and the equation of that line is this green line right here. Okay? Now, remember I told you we're trying to figure out what's f of 2. What's the y value when you plug 2 in for x? Well, as you can see, that's like right about there on the blue line, but I don't know. I can't tell, and I can't do it without a calculator. Okay? But since my tangent line is really close to my actual function at x equals 2, maybe we can estimate what f of 2 is using that tangent line. So f of 2, which is the actual value of my function at x equals 2, f of 2 is approximately equal to the tangent line's value at 2. And to find that, you just plug 2 into this function here, and I get 1. So f of 2 on my tangent line is 1, and therefore that's really close to what my ln function's value will be at that point. Okay? So that's the purpose of this. I picked a point which was really close to the one that I wanted. But the point that I picked was one that I know I can just plug in and get an answer for, because I know what ln of 1 is. Once I have that, I can create a tangent line, which I can use to estimate the value of the function at that point. All right, so step 1, find a tangent line at this point. Step 2, plug this number into your tangent line to estimate what f of 2 is. All right, now let's go ahead and take a look at another question here. Number 2 says, find the actual value of f of 2 using a calculator. So f of 2 is actually ln of 2, which if you punch that into a calculator, I'm going to do that really quick here. ln of 2 is 0.693. Now, as you guys can see, my estimated value is 1, but the actual value is 0.693. They're pretty close. They're not exactly the same because it's an estimate, but they're pretty close. All right, now the next question is f of x concave up or down? Well, at this point, that seems kind of like a silly question because you guys can see the graph here. Just take a look at f. Here's f. Is that concave up or down? Well, obviously that's concave down. But right now, I don't want you guys to think of it like that. I want you guys to know how to do it without a picture. So I included the picture just to help you understand what we were doing before. But now let's pretend that that picture wasn't there. Okay? We could still know the answer to this. Here's why. My estimate is bigger than the real value. So since my estimate, y of 2, which equals 1, is greater than the actual value, f of 2, which was a 0.693, that means that my estimate was an overestimate. My linear approximation gives an overestimate. And what did we say about that on our previous slide? When you have an overestimate, that means that your graph must be concave down at that point. Therefore, f of x must be concave down at x equals 1. And I said 1 because that's the point of tangency. Okay? This is the value I was estimating, but this is where my tangent line actually touches the curve. So since my estimate was greater than the actual value, my linear approximation is an overestimate, which means that it must be concave down. So just know that if you have an overestimate, it's concave down. And if you have an underestimate, then it would be concave up. Okay? So there it is. So let's review. I'm going to give you a function. I'm going to tell you to find a tangent line at a specific point. So you need to find the equation of that tangent line. And then you're going to use that tangent line to estimate what the function's real value is at another point. Then maybe you'll use a calculator, maybe not, but you're going to find out what the actual value of the function is, and by comparing your estimate with your actual value, you should be able to tell me whether the graph is concave down or up at that point of tangency. All right, so here's one for you guys. Go ahead and pause the video here and do steps 1 through 3, and when you unpause the video, you'll see the solution. All right, so here's the result. For step 1, we're finding the equation of a tangent line at x equals 4, because that's where they tell us the linear approximation is going to take place at. So my x value is 4. Plugging that into the original equation, we can find y. So y is also 4 once you plug that in. And then to find the slope, we take the derivative of this function and plug in 4, and we end up with 2. And so plugging it into our formula for a tangent line, we end up with 2x minus 4 is my linear approximation, or my tangent line, at x equals 4. Therefore, f of 4.3 is approximately the same thing as y of 4.3. So if I just plug 4.3 into my tangent line, I'll get a pretty good estimate, which is 4.6. Now for number 2, we're going to find the actual value of f of 4.3. And you do that just by plugging 4.3 into the original function. Now when you do that, you get this. Now as you guys can see, the actual value is just barely bigger than this. So when the actual value is greater than the estimated value, that means that your function is above the tangent line. And when your function's above a tangent line, that would mean that your graph would have to be concave up. And so here's a picture of the story. There's my function, f of x. My tangent line was at 2x minus 4. And the tangent line was happening at x equals 4. So that looks something like this. And as you guys can see, the tangent line is underneath of the curve, so it would give an underestimate. And at 4.3, which would probably be like right about here, those lines are so close that it's really difficult to even tell them apart. So my tangent line gave me a pretty good estimate, and it was only off into the hundredths of a value. So example 1 in student practice 1 is the real meat of what I want you guys to get out of this. Example 2 in student practice 2 is just to give you guys some different angles to think about this stuff with. Not quite as common of questions, but still kind of something worth pondering to help us develop and deepen the concept here a little bit. So try to think of these things as we go through them on your own. So the line y equals 2x plus 18 is a linear approximation of this function at x equals 4. So now just so you guys know, we have a function h. I don't know what it looks like, but here's x equals 4. So I'm just going to make something up. Let's say that h looks like this, right? Actually, I know that it can't look like that. Let's say it looks like this. Now, my tangent line at that point would look something like this, right? And so that's kind of what they're talking about. We have this unknown function, and this line, which is represented in green up there, is tangent to it at 4. All right? Now, you don't need to draw this picture because that picture is probably inaccurate. I'm just guessing. I mean, it could have a few different ways of looking, okay? So let's just leave it at that for now. What is h of 4? Well, since y is tangent to f, I'm sorry, not f, it's h. Since the y equation is tangent to h at x equals 4, remember how we said that the closer you are to the point of tangency, the more accurate it is? And when you're actually at that point of tangency, they're exactly the same? Well, since y is actually tangent to h at 4, and that's what they're looking for, then that h of 4 is actually identical to y of 4. And so even though I don't know what h is, I know that at the point of tangency, it has the same exact value of my tangent line, which I do know. So to find h of 4, I just need to find y of 4. And to find y of 4, all I need to do is plug 4 into my equation, which gives me 10. So now I have a point on my graph. I know that at x equals 4, y equals 10. So if I keep that point right there, I'd say that that's 10 and that's 4. Over 4 up 10, right? All right, next one. What is the instantaneous rate of change of h at 4? Now, another way of writing that is like this. The instantaneous rate of change of h at 4 is h prime of 4. But once again, since y is tangent to h at x equals 4, that means that h prime of 4 has to be the same thing as y prime of 4. In other words, what's the slope of my tangent line at 4? Well, y prime is just going to be negative 2. And so h prime of 4 would have to be the same thing as y prime of 4, which is negative 2. And once again, you're noticing I'm not using squiggly equals this time, because it's not approximately equal to, it actually is equal to, because instead of being close to the point of tangency, we're actually on the point of tangency. All right? Let's go ahead and take a look at number 3. If the line negative 5x plus 30 is the linear approximation at x equals 5, is this h of x concave up or down on the interval? Okay, now this is a really interesting question, so ponder it for a minute. Notice how I drew my picture here. why don't you guys ponder that for a second? You try to draw a picture of this situation and then see if you can come up with an example. Now, the way I drew it, it's concave down, but it didn't have to be drawn that way. I could have drawn it like this. Over 4 up 10. It could have been drawn like this. That way you still have a negative slope at 4, which is -2, right? So the question is, which picture is it? Is it concave down or is it concave up? You can tell because I give you one tangent line at x equals 4, and then I give you another tangent line at x equals 5. Okay? So why don't you guys see if you can kind of figure that one out for a second. When you unpause the video, I'll show you how I figure it out. Okay, so here's how I do it. So we already know some stuff about this graph, right? We know for sure, we know for certain that at x equals 4, y equals 10, right? And we know that it has a -2 slope at that point. So a -2 slope maybe would look something like that, right? Now, what about at -5x plus 30? Well, h of 5 should be equal to y of 5 because that's I'm going to call this y2 actually, so we don't mix it up with the other one. We'll call this one y1, and this one down here will be y2. So h of 5 is equal to y2 of 5. So if I just plug 5 in here, I'm going to get -5 times 5 plus 30, which is 5. So at 5, I get 5. So over 5, up 5, probably right about here. And furthermore, look at your slope at that point. It's -5. So this was -2, but at this point, it's going to be -5, which means it's going to be a steeper negative line. Now you tell me, if you just kind of were to connect these pictures in a way that those lines are tangent, and your curve grazes those tangent lines at those points, you could see that we would end up having to have a concave down function there. So to answer number 3, you got to do the same thing that we did on 1 and 2 here. We plugged 4 in up here to find h of 4, and we also found the slope of h at 4 using this tangent line. Now we're finding the y value and the slope of h at 5 using this tangent line. And that gives us enough information to sketch a picture which would indicate that this thing is concave down. Okay? So since the graph is concave down, would these tangent lines give over approximations or under approximations? And hopefully you can tell that since the tangent lines are above the curve, it would be over approximations or over estimates. Okay? So just stretching your mind a little bit with these concepts about what tangent lines are and how they're linear approximations and how you can use those to estimate the slope and y values of your functions at various points, and also understand what that tells you about the concavity. So here's one for you guys. Go ahead and pause the video here and see how you do. When you unpause it, you'll see the solution. So the final answer to this one is 7. Let's see why. Since y is tangent to g at x equals 1/2, that means g of 1/2 is exactly the same thing as y of 1/2. So if we just plug 1/2 into the y equation, we get 3. Also, since y is tangent to g at 1/2, the slope of g is equal to the slope of y at that point, which is 4. So if we're looking for g of 1/2 plus g prime of 1/2, that's the same thing as y of 1/2 plus y prime of 1/2, which is 3 plus 4, which is 7. Okay? So that's that. All right, guys, that was the last lesson for Unit 4, the last lesson for Semester 1, and then we got our test coming up. So nice job on completing a semester of calculus, and we'll see you guys in class for the last day of class this semester. Have a good one.